Now, another thing we wanted to look at is whether a silo group could act as a sort of a directing group for that 1,2 shift. So what happens if we have a ring here with a silo substituent next to the nitrogen? So we go to this ammonium ylide. Can this silo group facilitate the 1,2 shift? Maybe by way of this biradical to give us a product like this. That would be a valuable thing because, as you know, a carbon-silicon bond can be oxidized to give an alcohol by way of the Tamau-Fleming oxidation. And that would be useful because there are so many natural products, alkaloid natural products, that contain polyhydroxylation around this top part of the bicyclic system. And we could use this silo group as a masked alcohol in a way that would be much better than trying to have, let's say, an OR group in this starting material, because this would become a very labile aminal that probably would not stand up to the conditions required to form the substrate. Of course, the question was, would the silicon group stabilize the 1,2 shift? I'll just mention that there was some reports in the literature that actually did suggest that a silo group stabilized an adjacent carbon-centered radical. So the other advantage, by the way, of this is that there's methodology to introduce that silicon into a simple pyrrolidine starting material with high yield and with good enantioselectivity using Peter Beek's chemistry, where you have spartiene as a ligand for the intermediate organolithium reagent. And that with TMS goes in much better than 90% enantiomeric excess. We used phenyl dimethyl, which goes with lower EE, although still reasonable, and we can crystallize this to a much higher enantiomeric excess. But we went ahead and carried the 85% material through to the point of the ammonium ylide rearrangement by removal of the Bock group and alkylation with this bromide. And as before, this generates the spirocyclic ylide, and then it migrates with 90% retention by the silo-substituted carbon. So quite good retention of configuration to give us this quinolizidine product, which can be reduced at the ketone, oxidized at the silo group to give us, with very high diastereoselectivity, this dihydroxylated quinolizidine. We've also done the case where the side chain is one atom shorter. That gives us now an indolizidine instead of a quinolizidine. And this should be suitable for generating swainsonine in just a few steps. Okay, so in this first part of the seminar, I talked about making heterocycles, oxygen heterocycles, where the key intermediate is a cyclic ylide with a migrating group exocyclic to the ylide. I also talked about this series where the key intermediate is a cyclic ylide where the migrating group is part of another ring. So we have a spiro ylide, and when this group migrates, we end up with a fused bicyclic product. But there's a third way we can imagine putting this together. What if we have, we start out with a ring, we have the diazo side chain attached not directly to the heteroatom, but next to the heteroatom, so that what we form now is a fused bicyclic ylide. And again, an endocyclic migrating group in the other ring. But now when this 1,2 shift happens, instead of a fused product, we have a bridged product. And what's interesting to me about this is that our bridged product is bridged by this heteroatom, let's say an oxygen atom, but around the outside we have nothing but carbons. And if we can break open this bridge, what we've done is made a medium-sized carbocyclic ring, which we thought could be quite useful. So as a general strategy, we've got a number of approaches to natural products where we try to make a difficult ring, let's say an 8-membered ring, by making an easy ring. So if we start out with an existing 5-membered ring and we have the right functionality to make a second 5-membered ring, yes, we have a 5-5 system, but around the outside we have an 8-membered ring that's joined by a ring fusing bond. If we can break that bond, we're left with the 8-membered ring. We could do that in a fused sense. We could do it in a bridged sense. In either case, we end up with a functionalized cyclooctane. So in the specific example I just showed you, there's our easy ring. We make a metallocarbene that closes a 5-membered ylide, and then we do this migration from here to here, and we've stitched together these outer carbons to make a carbocyclic ring, using the starting heterocycle here as a sort of a scaffold for building the larger ring. And then again, the question is, can we open up this heteroatom bridge? So our thinking was dominated initially by targets like this. So dactylol is a simple sesquiterpene natural product. Phorbol is a diterpene, considerably more complicated. But what they have in common is a medium-sized ring, an 8-membered ring in the case of dactylol, a 7-membered ring in the case of Phorbol, that's fused onto at least one other smaller ring. And at the bridgehead, it has an angular hydroxyl group. And here, actually, 2 angular hydroxyl groups at 2 different bridgeheads. And we thought that that alcohol could come from a bridging ether if we had a way of selectively breaking that carbon-oxygen bond or that carbon-oxygen bond. So we thought these compounds might be available from structures that should be accessible using our fused bicyclic ylide methodology. So for dactylol, as I said, this would be what we thought we might make. If we could open this up, we would get to here and eventually to here. And this then would come from a precursor where we have a tetrahydropyran ring and at the bridgehead a diazoketone, which would make the corresponding oxonium ylide. And this would ultimately come from something equivalent to this chiral enolate. But let me just point out that our expectation here was that the metallocarbene would react with the oxygen to generate a 5-membered oxonium ylide, and then this sulfur substituted carbon could do a 1-2 shift up to here and break this carbon-oxygen bond, form a carbon-carbon bond, and give us this product. So we had actually kind of done this way back in the early 90s in this case. So here we have a pyran ring that has a side chain on one side and a phenyl group on the other side. And the idea was we would make the metallocarbene, in this case using rhodium catalysis. We would generate the fused bicyclic oxonium ylide, and now we have a benzylic migrating group. This migration should go to give us this product. And we saw this as the major product. We also saw a significant amount of this product, which comes from direct CH insertion in a transannular reaction. But we weren't too excited about this result, not only because it was not that selective, but also we didn't like having to use this phenyl group to stabilize the 1-2 shift. Not so easy to introduce and not so easy to process afterwards. In other words, synthetically, it's just not a very versatile handle. But also, we didn't know how we were going to break open this bridging ether. A little more recently, we looked at these systems. So here we have an acetonide ring, and it should be actually these methyls that are red, not these ones. And this acetonide ring will react with a metallocarbene to generate the corresponding oxonium ylide. And now in this case, this anomeric carbon will do the 1-2 shift, especially using copper catalysis. This goes in quite high yield to give us this new carbon-carbon bond and our medium-sized ring. So this is important because what that tells us is you don't have to have a phenyl group. You don't need conjugation in order to see an efficient 1-2 shift. This anomeric carbon will migrate quite effectively. So